Multivariable calculus. We're in lesson 16.1, starting the last chapter of our course, and we're getting into vector calculus. Look at our learning targets. I can sketch a vector field. I can find a gradient vector field. What's a vector field? Well, look at the top of the notes here. In general, a vector field is a function. It's a function whose domain is a set of points and whose range is a set of vectors. So here's what's happening. You could have a two-dimensional vector field, and you could have any ordered pair. Maybe it's going to be the ordered pair 2, 3, whatever. In fact, every ordered pair could be assigned a vector. What you're going to see is at that ordered pair, then, you will have a vector assigned to it. You will have a certain length and direction. You can envision a little arrow being drawn there. Likewise, you can also do this in 3D. You could say, look, you could take an ordered triple, and for every three-dimensional point, ordered triple, you can assign a vector. So what you're going to see is in your I, J, K direction vectors here, you can have functions, scalar functions, that would indicate, how you will arrive at this vector. There are many real-world applications for vector fields. You can see ocean currents right off the coast of Nova Scotia. You could say, well, for any particular point, you could say, hey, at that point in the ocean, the arrow is pointing in the direction that the ocean current is going. The length of it would indicate the strength of that current, perhaps. If the vectors represent a force, the vector field may be called a force field. And a force field could be something like a gravitational field. You can get into magnetic fields and all types of very wonderful applications. So let's just jump straight in and see one of the things that you might be asked to do. You might be asked to create or graph a vector field. And look at this vector field. It's negative y times I plus x times j. Writing it in component form is a little bit easier. It would look something like this. And first of all, wow, I just want to tell you, we could certainly go through some fundamental ordered pairs. Look at this. I'm just writing really unit ordered pairs. Everything is just going in the direction of one step away from the origin. And we could see where we're going. Notice the output, though. The output, when you plug in this point of an x comma y, you don't get a number coming out. You get a vector. You get a vector. So if you plug in, look, the x component of your vector, it's going to be negative of the y coordinate. So negative 0, that's just going to be a 0. For your j direction, you're just going to take the x coordinate. Look, you get the 0 vector. We're going to plot it later. Look at this. For 0, 1, well, your y is a 1 right here, so we'd get negative 1, and then we copy down our x, which was right here. Look, we're going to change the sign of y. So y is negative 1. Opposite of y becomes a positive 1. Look at that. And then 1 comma 1. Well, this is going to be opposite of your y, recopy your x. Opposite of your y, that becomes a positive 1. Recopy the x right here. Opposite of your y, opposite of 0 is 0. Recopy your x. Right here, opposite of your y, recopy your x, and look at that. So what will this actually look like? Well, I'm going to real quickly make a picture right here. We could say here's a 1, and right here's a 1, and right over here is a 1, and down here, this would be a -1. And, I don't think I got this quite far enough. The spacing isn't quite ideal, but you get the idea. 0, 0, the 0 vector, well, my goodness, it's going to have 0 length and 0 direction. But look, if we went to the point 0, 1, that's right up here. It's telling us to go left 1 and don't go up or down any. What will that look like? Well, at that point, 0, 1, that's going to be our arrow. At 0, -1, well, that's down here. That's this point. Draw a vector 1, 0. So go 1 step to the right. Don't go up or down any. At 1, 1, that's right here. Go down, go left 1 and then go up 1. So, actually we can put an extra space up here. So what would that look like as a vector? So at 1, 1, we'd say go left 1 and go up. So that's what your arrow is going to look like. At 1, -1, so if we go 1, we come down right over here, we're going to go up, right 1 and up 1. So, over here it could be our 2. So we're going to go right and we'll go up right here. Would look just like so. Hopefully you're getting the idea. 1, 0, well, that's this point right here, 1, 0. We're going to draw the vector 0, 1. Don't go right or left, just go 1 step up. Look at that. And then finally, -1, 1. Well, -1, 1 is this point right up here. We're going to go left 1, and we're going to go down 1. It's going to look something like that. So, guys, this is what a vector field could look like. You're showing that you go to any particular point, any particular ordered pair, and you will have a vector. I'm going to speed up example 2 real quickly. Sketch this vector field in 3D. This can be rather difficult to draw. Notice for any ordered triple, the arrow that you will draw, the vector that you will draw, is going to be in the k direction, and it's simply going to be the length of the z component. In other words, the higher up you get, the bigger z is, the longer the arrow will be. So take a look. I just drew some general points, like 2, 3, 1. So maybe we'll go 2 steps in the x direction, go over here, 3 steps in the y, and then we're going to move up 1 step. Well, your arrow will be a length of 1. By way of comparison, if you went to 2, 3, 5, up here would be 5, and all of a sudden your length of this arrow would be 5. And once you get taller and taller, that arrow will lengthen. By way of comparison, when z is negative, you will have a negative zk. That's going to be going in the opposite direction. So it can be rather difficult to draw this sometimes. It just takes a little bit of practice. Guys, in physics, one of the most famous equations that you're ever going to see is Newton's law of gravitation. Newton's law of gravitation states the magnitude of the gravitational force between two objects. You have a mass of little m and a mass of big M. Big M is generally the larger object. That force component, as we take a look at the magnitude of the force, it's just going to be m times big M times g all over r squared. G is a gravitational constant. R is the distance between two objects. So let's let M be centered at the origin, and I've drawn that right here. And let's have little m, the mass little m, have a position vector of x, y, z. So little m is right over here. So, we could look at it in that regard. The distance between the two objects, of course, is the length of vector x, isn't it? And if you were squaring that, you'd have the length of vector x squared. So that's really what we have right here. And we could even draw that in right here. This is your distance. Well, furthermore, the gravitational force on that second object is going to pull towards the origin. You know, obviously the smaller object is getting pulled towards the larger. That's what we see even as an object is falling towards Earth. Earth is this very large mass. If something is, in the air, it's being pulled towards the Earth. So the unit vector that you'd have towards that big object would be in the opposite direction of x divided by the length of vector x. So how can we find this force vector? Well, we can say plain and simply right now, we know it's going to be m, capital Mg, all over r squared, but we just said r squared is just like we said right here. It's the length of vector x squared. But remember, it's in this direction of negative vector x all over its length. This is our unit vector. So what do we get here as we work this out? It's negative m, capital Mg, all over the length of vector x. Well, you can see if this is squared and if this is one more, you're going to have that cubed. And then we're going to say times vector x. So another way we could write this is to say that in component form, we could say, look, we're going to have this is our magnitude, right? And we could very well say, look, if you've got an x component right here times j, that's going to be your x. You'll have negative m, capital Mg, all over the length of vector x. Well, look in your y direction. We just wrote that as a y. And then we'd have negative capital Mg all over. And all these are cubed, pardon me. Just as we saw right there. And there you have it. That would be in component form. Now, a picture of this gravitational force field, you could look at page 1084 in our book, and you can see a nice depiction of what that gravitational field looks like. Wrapping this up, a gradient field. Well, the gradient, which is the derivative of x times I and the derivative of f with respect to y times j, is your gradient, and this would be a gradient vector field. If you're assigning a vector in this regard for any point, then you've got a gradient vector field. So let's go ahead and find this gradient vector field for example 4. Well, we could say, well, it's f sub x times f sub y. And what's the derivative with respect to x? Well, it would be a 2xy. The derivative of negative y cubed is 0. Take your derivative of a y here, you get x squared minus a 3y squared. What are we seeing? We're seeing, you give us the ordered pair, give us an x comma y, and you will have a vector. This is a vector field. So that's rather nice. That's a gradient vector field. One last thing. A vector field is called conservative if it is the gradient of some scalar function. So as long as what's generating your vectors is a gradient, then we call it conservative. The function f would be called the potential function. Not all vector fields are conservative. Many in science are. The gravitational vector field, in fact, is the one that we just finished up. So that is lesson 16.1. Good luck.